basically, we are today looking into what we are doing here at 5.2N with web processing. We will do an introduction to the overall concept, take a closer look at standardizations, and after that, yeah, look into an example application and how this is done technically with the software and the concepts that we presented early on.
I'll kick this off. This is the agenda. Matthias mentioned this. First, yeah, we introduce you to web processing, to the standards and WPS, and also the API processes that's coming up. I will talk about software solutions that are out there, and then Matthias will get his hands dirty and shows some really nice stuff that we can do with our JAVAPS. Okay, so why are we doing this? Why web-based processing and WPS? So yeah, first of all, this is one of our main focuses here at 52 North. We have one big block for yeah, sensor web enablement, geospatial sensing, a broader sense, and then that's more or less gathering data, you can say, and then the other block is the processing of this data. So we're doing this using desktop apps, web apps primarily, and we look at things like spatial data infrastructures and big data. So geoprocessing, we start with raw data. There's lots of data out there gathered by, I don't know, temperature sensors, water gauges, things like that. So that's there. And the first step would be to do some processing and add some value to this data. So going from the raw value of such a sensor to a pre-processed value. And then we can also go further with the processing and create some real information products out of this. For example, weather maps or yeah, some gauge maps for water depth or something like that. Yeah, in the early days, this was done by people on their own desktop, and they had the input data for the processing there, and yeah, the output data was stored there as well, and then maybe printed into some paper map or stuff like that. And yeah, we are more focused on the web service approach. And here's an example of a project where we're also participating called Rieke. So there we deal with earthquake events, and then the scientists start a shake map computation to create a shake map, which is a map showing the intensity, the estimated intensity of the earthquake. So, and they did that on their computer. They have specialized models for that. And now if you wrap that in a web service, which we call shake map service, we have certain benefits. So we can access this service using web applications. We can access this using desktop applications at the same time. And also other web services can access this service, like in the service chain, for example, using this shake map to compute additional things. And another step would be to store the outputs or the shake map directly in a data service, which then can also be accessed by other web services. And all this is done using standardized APIs and also data formats. Okay, so a short overview about the whole, yeah, not the whole, but the service landscape of the OGC, so to say. We have different services. Mostly they are data services, like the web map service. for accessing maps as images in different formats. Then we have the coverage service that gives you coverage data, multidimensional data, for example, in a GeoTIFF format or NetCDF. The web feature service for vector data, features in the GML format or as shapefiles or GeoJSON. The sensor observation service gives you sensor data in the observations and measurements format. And the thing we are mostly talking about here in this tutorial is the web processing service, WPS, that lets you process this data and run simulations and lots of other things. So again, why are we doing this? So I have my desktop PC, and now the setup of the software that I'm using is very complicated. And so instead of doing this setup on each computer for each user, you can think of doing this once in the web and make this complicated software accessible using a web service. And then you directly have the benefit that each user can directly use this on his own PC without a complicated setup. Another thing that's very important is the data. So in the earlier approach, I showed you that input data for the processing was on the same machine, the same desktop machine. But there's lots and lots of data out there coming from satellites. That's just massive, and you don't want to download this to your desktop PC and process data there. And you can think of tightly coupling of the processing with the data that's out there. And processing large amounts of data also is very costly. Thinking about resources like CPU power and stuff like that. So putting processes in the web, you can use a massive server farm for your computation and just trigger the processing from your desktop PC and also download the resulting data from the server farm. Another thing is that I want to use different technologies. We call that processing mashups. So really, I would just want to use a bunch of stuff that's out there for processing. And this would be also very complicated to do on your desktop machine. So that's another use case for geoprocessing in the web. Baseline is I want to reuse processing in different environments. Okay, so now a few words on standardization for geoprocessing. I was already mentioning that the WPS web processing service standard of the Open Geospatial Consortium. The first version 1.0 came out in 2007, and since already 5 years, there's a second version out there. And the web processing service delivers a standardized description of geoprocessing functionality, which we call processes to be short, with an identifier, a short description what this process does, and also what input and output parameters this process takes. It defines service operations for description and execution of these processes, which also can be done synchronous, which means you're directly waiting on your result, or asynchronous for longer running processes, where you can request status updates and then finally the results of your process. There's some software out there that's using WPS, open source and also closed source software. And I think I will talk about that a bit later on. So that's an overview about the things you can do with the web processing service, the basic operations. So We have different clients, desktop apps, web apps, or spatial data infrastructures, cloud environments, and a number of processes which can be run in one WPS or also in different WPS instances. And just a quick overview about the operations. I will talk about that now in more detail. So first of all is the get capabilities operation, which primarily delivers a list of processes that you can use that this WPS is offering. So this is a get request. You can also use post, but for simplicity, I think the get is more widely used. And this returns a description of the WPS, so some basic information, also about the endpoints for the other operations, technical request mechanisms, so what is used, get a post, for example. Also information about possible access constraints by the provider. And then, as I was saying, the information about the offered processes, along with the title, for example, and the description. Okay, so now we have the list of processes. We can look at the description and see what fits our needs. And now we do the second operation that's called describe process, where we want to get more information about the process, more detailed information. So this can also be done via get or post. And yeah, so the information returned is the ID and also the data formats that are used as input for this process. So there can be default data formats and also additional data formats. For example, you can have input data formats like GML, and also the process input can be sent to the server using GeoJSON. So this is information that you get here. Also, the outputs are described, what you can expect to get by this process. And that's more or less all the information that you need for the execute operation. And there you use the execute endpoint, send your input data using XML, and hopefully get back a processing result. So this operation uses only post, at least in WPS 2.0. And you do that, of course, on a offered process. And the requests must contain the ID and input parameters for this process according to the description. And you can also define the outputs. For example, if the process offers multiple outputs, you can say, I just want output 1 and not the second one. The results can be returned directly in the response XML, or they can also be stored as reference to a web accessible resource. So I was talking about the synchronous and asynchronous, but I think we see that later also in a sequence diagram. Words regarding the transfer of the input data. Now I was talking about large amounts of data, and we have several options to do this. Transfer to the web processing service. The direct transfer, so within the XML, which of course is not feasible for large amounts of data. This is feasible for small inputs or text-based inputs. For example, you have a small GeoJSON feature. This can be sent directly in the XML request to the server. More common use case would be the reference to a web accessible resource. So you just specify in your request, in your execute request XML, for this input, you can find the data at this URL, and then the WPS will fetch this data and process it. The third option, also very common when you look at Earth observation data, is that the WPS and the data lie on the same or run on the same server, and you just specify what data you want to use. For example, you can specify the ID of a satellite image, which is then used by the WPS directly with no transfer over the web needed. All right, so synchronous execution. Show you the sequence, how this works. So the client sends a request, execute request. WPS receives this, is processing. The client waits for the response, so it has also to keep the connection open. And after the WPS is finished, it sends the results back via the same connection. So WPS receives this and can use it. So then we have the asynchronous execution, the push model, where the client also sends a request, WPS receives it and processes the data. So the client can do something different in between. And the WPS sends back the result to a URL, to an endpoint that the client has specified. So there's no need to keep a connection open. This is, of course, very useful for longer running processes. And this is something actually that's not implemented in WPS or specified in WPS, but in the API processes. And I will talk about it in a bit. So that's the asynchronous execution approach of WPS 2.0. So we execute using the async execution mode. Then we directly get back a document containing the ID of this execution, which is also called job, and the status, which is in this phase accepted. So WPS accepted this execution. And then the client can use this job ID to request the status of this execution. So this would be the asynchronous execution in the pull-based mechanism. So the client really has to pull the status location so long as until the execution is finished, and then the client can get back the result. But it has to take care of the getting the status itself. Okay, so now we are coming to the OGC API processes. This is something that's currently in the standardization process. It's gone quite far right now. The next step is a request for public comments for this emerging standard. There are already several implementations available for testing, which are all listed in this URL. And this is a modular standard. So we have a core, which is also shown in this UML diagram. And we also have extensions for this API, for example, a transactional extension. So why are we doing APIs all of a sudden? So the existing OGC standards or specification, WPS 2.0 is no exception, define a SOAP XML binding as interface. With there are some exceptions, but most of the services or specifications do that. And so the REST paradigm is out there also a very long time, and more or less everything is REST nowadays. And also using JSON instead of XML makes the whole thing much leaner and easier to use. So we have a focus on resources, not on the operations. for example, these that I described earlier. And we use the standard HTTP operations to create, read, update, or delete resources. So, and the OGC API processes originated from a OGC engineering report. This is also a couple of years back, I think 4, where several REST APIs for OGC services were outlined. And since then there was some kind of process, and hopefully end of the year the OGC API processes will be released in the first version. So regarding the resource model, the resources of the API processes are based upon the general process model of WPS 2.0. So we did the new API very close to WPS 2.0. The new thing is this hypermedia approach. So you really can use links in the resources to get along further down the road, so to say. So you can use the landing page to get to the process list, and from there you can get to a single process description, and from there you can get to the execution endpoint. So these are the resources and endpoints that are defined. So landing page is just the base URL. The process list, you attach /processes. Single process, you have to attach the process ID. You can also have a list of jobs, so executions for this process, which would be a GET request to the /jobs URL. If you post to this URL, you create a new job, you execute the process, and if you then attach the job ID that you get back, you can get the status info. And then the final and the longest URL is everything, and then attached results to get the outputs for this this process, this job. So yeah, you can see here that this API more or less really maps to WPS 2.0, but at least we think it's a very lean and straightforward definition of the endpoints. And so we're eager to see what the public has to say about this. Okay, so one word about JavaPS REST. So that's one of our software components that I will shortly explain also later on. This is implementing the API processes. We have a GitHub repo for this, and also an example instance for testing. And everything I show you on the next slides uses this example instance. So look at the landing page. So the base URL, there's no defined pattern for that. So that can be everything that the service implementer wants. And if you access that using GET, HTTP GET, you will see the landing page resource, and that contains some general service information. For example, also the list of conformance classes that the server, the API conforms to. That doesn't need to be only OGC API processes. That could also be other APIs, at least parts of other APIs. And the most important thing is, of course, the link to the list of processes. So you can see here. The process list is not so spectacular. It's just really a JSON list element containing short descriptions of the processes that the API offers. For example, the title can also have some keywords and metadata. The job control options, so whether you can execute this process synchronously or asynchronously or both. Where the outputs can be stored, whether they can be returned directly in the JSON or stored as reference. And there you also have the link to the detailed process description, which you can see in the next slide, actually. So it's a bit larger. And as in the described process operation, this returns detailed information about the process, and yeah, most notably the inputs and outputs that are that this process needs, and also the outputs that it produces. So I hope this is readable. I mean, it's just a JSON element having a list of inputs and outputs. So for simplicity, we're just using one here, a complex input and complex output. And this needs to have a format specified. So the data format that we also know from WPS. Yeah, the hypermedia approach. So we also have a link here to the execute endpoint, which is the same URL and then just /jobs. Execution. You need to send some JSON to the execute endpoint. It's using post. And yeah, this creates a new resource. And in the execute JSON, you specify your input data, which can be inline, as you can see here, or this could also be a reference. And yeah, you specify your outputs. So this is very alike to the XML-based approach of WPS. So the default execution mode for this API is async execution, asynchronous execution. And then you get back HTTP 201 created, and you get back the link to the just created job resource. So, and if you access this job resource, you see a status info document. As you can see here, in this case, the execution was successful. And then you also get the link to the results back in the status info. For synchronous execution, yeah, this very short slide. So you have to wait for the result, and then you directly get back the JSON containing the outputs, if it was a successfully execution, or you get back an exception if there was some kind of failure. So, and the result document looks the same as if you would request the results of an asynchronous execution. It's really quite simple. You just get back a list of the outputs. Okay, a nice thing that most of the implementations are test clients. So you can access these endpoints specifying different accept formats in the accept header, and if you go to the execute endpoint and specify I want to have HTML back, then you see this test client that we have, where you can load some example requests and also execute the process. So that's very nice for testing. Feel free to access this URL. The processes don't do much, so hopefully you can't do anything wrong there. Just play around if you want. Okay, so we also have a couple of example applications listed here. So one of the earliest adopters of WPS is the United States Geological Survey, USGS. They use that very much internally, so for giving researchers access to their data. But they also have this geodata portal, GDP, where you can download data and yeah, mostly just have to specify a area of interest. But yeah, they're using WPS for that, and yeah, we've been in contact and discussion with them since a very long time. So another thing that we did was in the context of the TAMIS project. So this was dealing with yeah, an information system for dams in the Wupper region in Germany. And yeah, WPS was also used there to execute models, which yeah, before this project were only executed on desktop machines, and we brought that to the web. Yeah, and they also were used for spatial interpolation and linear regression. So very wide use of WPS here in this project. Another project that's I think still ongoing is Vacodes, and WPS was used here yeah, as a means to process or to create Earth observation products in an automated workflow. So the user had to specify yeah, the input data, the Earth observation product for the input, and the method or the process, for example, NDVI. And then this Vacodes system yeah, downloaded the data, and when this was finished, download started processing, and then delivered back the final EO product. Okay, I mean, there are more things out there, but of course we don't always hear about them actually. So these are some things we do ourselves, and yeah, with the USGS guys, they approached us, and then we had some very good discussions. So that's why we just had 3 things here. So a word about these server implementations and also client implementations. Currently, the OGC lists 69 implementations for WPS 1.0 and 2.0. There are commercial ones like Esri, Intergraph, and others, and open source implementations. So our implementation is open source, and then there are the guys from PyWPS and Zoo Project and also GeoServer. So the biggest players, I think, in the open source world. So our WPS is currently in a beta version 4.0. So that's just our internal 50 to North versioning. So yeah, this supports really not all, but most of them, most of the features and operations of both specifications, so 1.0 and 2.0. We have a couple of processing backends that we use to generate processes. So, for example, we can use GRASS processes. Yeah, something called Sextante that's out there. You can use R, and of course, you can directly use Java, Python. Yeah, so a really nice feature of our WPS is that you can upload R scripts using a web UI. And yeah, then you have your R scripts directly running as a web service. One of the widely used features, I guess, or the most used features of a WPS. And another thing we also I have included in our WPS is a set of parsers and generators for different data formats. So that comes also very handy, especially if you write your own processing functionality. Another thing we have is something called JAVAPS. So that's currently in version 1.5.0. Yeah, that's a completely new implementation of WPS, or of a processing framework, let's say, using state-of-the-art technology. This supports WPS 2.0 and also the upcoming OGC API Processes. Yeah, and I think a focus of this JavaPS processing framework is really the deployment of new processes. So this would be the transactional extension. And we also have a set of parsers and generators for the data formats for this JavaPS. A word on deployment patterns for our processing frameworks or processing servers. So you can, of course, extend the WPS directly. So writing, in our case, new Java classes, for example. You can use your custom binaries, for example, your custom model, which comes mostly with a configuration file, and yeah, encapsulate that in a WPS process. WPS can be used as a rich data interface, and you can deploy annotated scripts. So and now I will talk about that in more detail. So yeah, one of the things that at least I use mostly is writing new algorithms in Java for our WPS. So yeah, this is of course quite useful because you can directly make use of the input-output handlers, these parser generators. Yeah, so you write your algorithm and just throw your jar file in your WPS, and then you have a new process, which is quite nice, but of course doesn't work for your binary files that you may have. There you will write some kind of wrapper process, for example, that executes a shell script, which is your model, your binary program in this case. And you mostly have to specify where the inputs lie for this script, and also where the outputs should be stored, so that the WPS can save the inputs in the right location and also get the outputs from this script and return this to the user. Rich data interface, we see this as as an interface for large data stores. So I was also mentioning this earlier. We have this massive amounts of EO data, and mostly this is lying in some data store. And WPS can be used to create sort of dynamic views on this data, for example. An NDVI could be used, could be seen as a view of the data. Data is there, but I just want to see the NDVI of this data. And I also mentioned that you don't really have inputs for this data, so you just specify the time frame and the process, like in the VDI, and then the WPS can access the underlying data store directly and create your product, your result. So deployment of R scripts, which is really a nice feature. All you have to do is add some annotations in your R scripts, which are comments with specialized keywords. And then you can really upload that to our WPS. And using the web interface, and then you have web service created out of your R script, which is really nice and widely used. Right, so you can see annotated script with the specialized keywords. So really not complex, and yeah, a nice feature. So client implementations. There are a couple of client implementations out there from us, from 52 North. We have an extension for ArcGIS that we did together with Esri. And yeah, of course, ArcGIS is proprietary, but our client is open source. And we have a couple of JavaScript libraries and client, actually. I will show that also in a minute. The QuantumJS plugin, I think, is still out there also for a while now, and also open source, really nice. And there are always custom clients for specific applications. For example, this geodata portal of the USGS that I have shown you earlier. So this is a look at the WPS NG JavaScript client. So this is using our WPS.js library, which is really just used for creating requests and reading the responses. And the NG client has also a nice map and some features you can draw on the map and use the features directly as inputs and stuff like that. It's based on Angular and also used in several projects here. The ArcGIS client is also, I think, quite nice. So this is really focused on seamless integration into ArcGIS. So we have added a new item under the GIS servers catalog tree at WPS server. And this is opening a custom dialog that we created, which also should have the look and feel of the other dialogues, for example, adding a web mapping service or something like that. So they should look very similar to users of ArcGIS. And yeah, you specify URL, and in this case, it's just one process, but you can also have a list of processes and select them. And then the nice thing is that really we have geoprocessing tools created for each WPS process, and they are listed in the WPS toolbox. And yeah, they can directly be executed using a standardized ArcGIS dialog. But the nice feature is also that these geoprocessing tools, as they are really standard ArcGIS geoprocessing tools, can be used in the model builder. So you can just create your workflow, and yeah, then it will access the remote WPS server. So it's really a nice feature, and this is just a result of this process. Yeah, hotspot analysis of 911 calls. Okay, and I think with that, I'm finished.
I think the next part is a little bit more hands-on, a little bit more practical. So we now have all the basics, which were presented by Benjamin. You know what the web processing service is. You know what the overall idea is. You can see me now again. Great. And yeah, so maybe first of all, just to do a little technical check. I think, Benjamin, you need to stop to present, and then I can start presenting.
Stopped.
Looking good. So if you can see now the client I'm sharing, hopefully. Perfect. So yeah, just using this as a technical test. So as Benjamin was already on that end, I just briefly want to show you how this web client looks like. So it's map centered, and I can select from a list of predefined web processing service instances. And for example, we have developed some nice processes in the Riescos project. We already saw some of these Quake ML processes, earthquake-related processes, and I just briefly want to show you how this looks like in an interactive environment. So the client has this very nice feature to select all the default values which are defined, and then I simply need to add those inputs which do not have a default. In this process case, it's just an input bounding box. This process will then query a pre-done simulation or pre-established database with historical earthquakes, and yeah, I'm simply able to define an area of interest. Let's say I want to check the Valparaiso area here in South America, and everything is set then. Here I can see on the right side, if I have this blue mark sign, then the input is valid and should work perfectly fine with the process. There are a lot of inputs. For most of these, the default values are fine. The domain experts might want to tweak a little bit here. For example, you have the magnitude, minimum and maximum you want to consider for an earthquake. Z min and max should be the altitude because it can also be an earthquake in the sea, and different other stuff that I can configure. But I just want to show you how this works. I have my output, which is defined as a GeoJSON output, and then I can go over to the execute part, and everything is predefined already, and I can simply click on execute. This should work. Just checked it beforehand. Takes a little while, but after that, yeah, I just get one earthquake in this area, and I can also take a closer look because it's GeoJSON. We are able to render the properties of this GeoJSON feature very easily, and I can see that I have an earthquake here. I guess this time is a little bit broken depending on the time frame because it's an historic one, probably before 1970, which is the starting time of the Unix epoch. So this is broken a little bit, but I guess in the source database it's fine. We have a magnitude of 6.65, so pretty straightforward. I can take a look at the outputs of my process. So yeah, just introducing this. I will come back to the client later once we have our self-defined process in one of our web processing services or OGC API processes. So this brings me back to the slides. I will not do the presentation mode. I hope this is fine because I have multiple screens. So yeah, I will take a closer look together with you guys on how to develop a new process, bring this into the JAVAPS, so having also the OGC API processes interface at hand. And we will use Python for developing this process and also Jupyter notebooks. So very well-established approach. And at the end, we will be able to have this process on the web and being executable remotely. So first of all, a little of background or a motivation where this work comes from and where this feature comes from. We have worked in this area of cloud-based processing in many OGC testbeds and many different OGC initiatives, like also pilots, Earth observation pilots, where the sponsors of these testbeds were interested to bring processes or algorithms working on large sets of data into the cloud environment. So users do not need to download the data to their local machine and execute a heavy weighted process. Shifting this to the cloud was essential in this in this environment. And as you can see here, we also have connections to different clouds. So for example, you can run your process on cloud A and the data is sitting in cloud C, maybe has a very good network connection to it. And we can provide a web processing service, or in this case, an OGC API processes interface to the external world of the cloud and access. So all the functionality is hidden in all these layers from the web. And technically, the approach is as follows. We developed a mechanism to be able to deploy new processes to a running instance of a server, in this case JAVAPS, and we are using Docker as the main technology for this, because Docker allows us to create reproducible processes in whatever environment. It works the same way on my developed machine, and it works the same way in a cloud environment. So there are no pitfalls to environment constraints, to missing libraries or anything like that. If I have a Docker image pre-made or set up in the correct way, then I'm able to execute this process in any environment. So the idea is to deploy this, reference a Docker image within that, and then I can use the normal approach like Benjamin already explained. I can use describe process, and then I can execute the process again after that. And yeah, this is basically what we are doing now. Yeah, the concept is we wanted to find a good way on bringing processes which are developed maybe by domain scientists or data analysts or data scientists into the web. And one of the major technologies here is Jupyter Notebooks, of course. An alternative is R, R notebooks or R Markdown scripts. But at the moment, we focused on Jupyter Notebooks, and that is what we want to present, or I want to show you now. So the idea is we have 3 steps. We develop a simple process in Jupyter Notebooks. We make it executable in an environment-independent way, and then we host it in the cloud close to the data. This process is not data heavy, which I will show, but the idea, of course, is that we can use this for data heavy processes as well. Okay, so the approach for these 3 steps behind the idea is, for the first step, we use Jupyter Notebooks to develop a very simple process. In the second step, we make this Jupyter Notebook executable in an independent way. We use Docker with a Python kernel for this. And some more technical details I will show later on. And at the end, we will host it. We use the OGC API process with a Docker execution backend and this transactional interface Benjamin briefly introduced. So we have the possibility to register new processes on the fly without needing to restart the server or configure it in another way. Okay, let's get into it. I have put links in here because you can download the slides later on and then use these links. But for the moment, I will use my local environment. I will start with the notebook. I've launched a notebook server here on my local machine, and then I've prepared this, but I will walk you through this. I've prepared a very easy notebook creating a geometric or geographic buffer around a GeoJSON input. So first of all, we need to import some libraries that we want to use. In this case, we use GeoPandas, which is very well established in the geo world. And yeah, then we define our basically inputs. And here you can already see it relates a little bit how to a web process in the web processing service or the OGC API process is established. So we have some sort of inputs for our process, which is on the one hand the GeoJSON file, and then we define a buffer around this, which is used later on in the process, and we also define an output file name. And yeah, let's just run this. This works fine, this works fine. And the next one is reading this file. And yeah, this is done with GeoPandas, and we simply get the first feature in this GeoJSON file and output the geometry of that. So it's a point. This is the 52 North headquarter. I can briefly show that to you. Oops, sorry. Let's open this up in GeoJSON IO. I don't want to recover my map. And then, yeah, this is 52 north in the nice area, south area of Münster in Germany. So yeah, this is our input. And this is read now into my Python or notebook script. And then I want to find out in which UTM zone I am in order to apply a meaningful buffer around that and not based on longitude, latitude, because that is obviously not working for every point on the globe. It can work maybe near the equator, it can work, but beside that, it won't work. So we use a projected coordinate referencing system. I used a little math magic tricks here to identify the correct zone. We don't need to get into that, but I'm in zone 32 in the Northern Hemisphere. And after that, I basically use GeoPandas to create a buffer around that. It's pretty straightforward because GeoPandas has built-in capacities for that. First of all, I make a copy of my GeoJSON. I retrieve the geometry. I convert it to the UTM zone coordinate reference system, and then do my buffer with the radius meters I have defined before that. So 1000 meters. After that, I transform it back to 4326 EPSG, which is the default for GeoJSON, so that all clients can work that in an interoperable way. Pretty straightforward stuff. Do that, and then I do a little plotting here. It's not on a map, but at least we can see I have a buffer with latitude and longitude. And at the last step, and then we are already done with our process, I'm writing this to an output file. And then you can see in my directory, this is all done locally. I have a buffer GeoJSON, and this looks like that. And if I put that into my GeoJSON.io web app, then I see my buffer is 1 kilometer around the 52 North headquarters. I can, of course, adjust this to, let's say, 10 kilometers. I rerun my full kernel from start to end. And at the end, the file or the plot is generated. You already can see that there are different values in latitude and longitude. It's written to the file again. I need to reload this, and then I have different coordinates. I can visualize this, and then my buffer is 10 kilometers. So pretty straightforward stuff, but the overall idea here is that I have a Jupyter notebook, and I have a set of parameters which I can switch or adjust to my needs. And yeah, then the output is obviously also adjusted. So this is the first step in our our process development and bringing this into the cloud. So you would ask yourself, okay, now I have a very nice interactive notebook, but when I run it on the cloud or in a non-interactive way, how can we define the parameters? Because as a human, I can't interact with the process in any ways because it's done all on a backend server. No one will interact with that process. And there is a very nice library developed actually by Netflix, because Netflix is doing a lot of their backend work with Jupyter notebooks. They developed Papermill, and Papermill allows us to parameterize our notebook and yeah, basically set the parameters and then execute the notebook with these parameters from outside. So pretty cool. All you need to do is add a little tag here. And what will happen then is I can simulate this here. Papermill will do nothing but post cell below. It will create another cell behind this parameter cell tag and change it to the parameters I've provided from outside. So maybe something like this would happen. So in a programming language way, these variables would have just been overridden with new values. And this is everything Papermill does. And then it executes, obviously, the notebook as well. So this is really cool, very lightweight, and very, very easy to use. And the next step is then, once we have this with Papermill, I will show that later on a little bit more. We need to find a way to make this executable on every machine, on every computer, and every cloud environment in the same way. So the idea is to have a Docker image prepared that can do this. There are already a lot of Docker images. If you don't know Docker image, it's basically a concept which makes virtualization a lot of easier. Maybe you know VirtualBox, maybe you know VM, or what it's called, the other thing, but you know VirtualBox, which is basically setting up an operating system on your operating system. Maybe you want to run a Linux on your Windows. Docker is doing this in a more lightweight way. It's not providing the full operating system, but it is providing what is added on top of that. So it's a virtualization concept. If you want to read about that, there are lots of good resources online. I will not go into detail, but for our case, it really allows us to set up this Python environment and make it executable on any machine. So there are some nice basic images for Python environments, Miniconda 3, for example, which allows us to set up libraries at build time. And then we just need to define the libraries we need, GeoPandas, and make it executable via the Docker execution command with Papermill. And we have done this in this way. We are using, I hope it's not too small. Ben, maybe can you confirm? Can anybody read this? Can you read the texts I'm sharing? Make it larger, okay. So that should be better. Cool. All right, so yeah, we are using this base image, which already has a Python kernel defined. Then we are using an environment file, which defines the Python libraries, which we use in our notebook and activate it. So it's a little bit technical, but you don't need to know about that. Then we are adding our Python Jupyter notebook, because that is the basic execution process. And then we are defining some environment variables, which are later then used by the Java PS to provide the inputs to this notebook and to execute it with Papermill. At the bottom, we can see the Papermill command, which is basically a command line execution, pretty straightforward, Papermill command. We use the notebook as an input. It always requires an output notebook as well. It's not so important for us, but you could take a closer look on the individual cell executions afterwards if there goes something wrong. And then we use this P thingy here as a parameter to define all the inputs that we use within our notebook. And this is basically how it is set up. Pretty straightforward, nothing too complex. And if we build this Docker image, we are able to execute our Jupyter notebook within Docker. And I will just do that here locally to illustrate or to demonstrate that it works. I simply bring up my Docker, and yeah, some stuff is executed here. And this is a part which starts from Papermill here, input notebook, output notebook. And then you can see there are 9 cells executing, and at the end, all 9 cells have been executed. And it works as expected. No big errors, just some caching things, but that's nothing important for us. It works as it should. And now we have a Docker image, which we can then upload to maybe Docker Hub or something like that, make it available on the web, or upload it to the server where our web processing service will run later on. And then we can define a process that executes or uses this Docker image, and in the same way also uses our Jupyter notebook for the execution of the process. So this is basically the next step. And I hope it's not too much, but if you have questions, we can catch up later on or in one of the coffee breaks. So the next step then is, again, going into the direction of OGC API processes. So we need to have a way on describing how this Jupyter notebook should be, or this Docker image should be executed from our OGC API processes backend. And for this course, the OGC has developed a best practice, I would say. It's not an official standard. It's an extension to the OGC API processes, and it's called ADIS, whatever you want. It's abbreviation for Application Deployment and Execution Service. And basically, it's a combination of the transactional API, which Benjamin already introduced. So we can register processes, we can delete processes, we can update processes via a web interface, and the execution units concept. An execution unit would be a Docker image, like I just showed, or it could also be another programming language environment like RStudio, or maybe a complex workflow engine like CWL, something like that. But it's an abstract concept, and it defines how an underlying process should be executed. In our case, it's a Docker image, so we already know how this will be done. And then in order to bring all this together, we define an application package. And in this application package, we define the inputs of the process, the outputs of the process, and the execution unit. So it very much looks like what is already there in OGC API processes and in WPS. You will know everything here. We have inputs, defining the geometry to buffer. We have another input defining the buffer radius in meters. So you already see this reflects what we have done in the Jupyter notebook. And we have an output, a buffered output. We have some additional metadata like should it be executed asynchronously, should it be executed synchronously. These are just hints. We don't need to follow that at the end, but these are the defaults then. And then we have the execution unit, and we say the type is Docker, and then we reference the Docker image. And as you can see, I have, I can build this image pretty straightforward. And at the end, you can see the last output of this command is, it takes a little while, defining the environment variables. And the last step is the command. And after this, we have a new version of our Docker image. And you can see this is the same name as referenced in the application package. And in this way, we define how our process will be executed. So at the end, you will see all the inputs and the outputs occurring in the OGC API process output again, in the same way as we defined it here. And I will simply demonstrate that. We have an ADIS running on one of our test machines. You can see what Benjamin already presented. This is a landing page of the API, and we can take a look at the processes. Unfortunately, our ADIS does not have any processes, but we will change that. And this can be done with very simple HTTP requests, like already introduced by Benjamin. And we use, for example, a post request to this endpoint, which is basically the same as this one. I hope this one is not too small, you can read it, but it's the same URL as here. We define the content type, and then our post body is this application package I just showed. So copy paste, it's the same. And then I can send the request. Hopefully everything works. I get back an HTTP 1.1, create it, and I get back a location. And then I can get back to my browser and see if it works as expected. If I reload this page, this is a process endpoint, then I have a new process available. I can take a closer look at this process, and I have all the inputs as defined in my application package. So this is the basic work of the transactional interface. What we don't see here in this process description is our execution unit. So this is not of interest for anybody using this API. Only we as the developer of the application package know that at the end, when we execute this process, the Docker image is executed to do the job. Okay, so now we have our process available. And the next step would be to execute it. Let's close this one. And again, we define our inputs. I used the same GeoJSON as I just showed to you, using Münster as the input, or the 15 North headquarter. We use this time 15 kilometers as the radius, and we want, of course, to have an output again. I can do asynchronous execution as well. Let's do this. Execute the request, and then I get back a location link where I can check if my process is already has already executed successfully. Let's check it. Status successful. That looks perfect, and I can retrieve the results with clicking on one of these links. And again, here I have a reference to an output which I can download now, and this should be the buffer GeoJSON. That looks perfectly fine. I can copy this over and visualize it in GeoJSON IO. And maybe it was the same radius. So let's remove it. Let's reload this. The page was broken. Oh, this doesn't work as expected. But believe me, it is a valid GeoJSON, and I will demonstrate that with our client as well. So getting back to our slides, basically, we have achieved already what we wanted to achieve as we had the idea. We developed a Jupyter notebook, made it executable from the outside using parameters with PaperMill. We created a Docker image, which is able to execute these notebooks, having the right Python libraries, using parameterizations with PaperMill. We defined an application package to define the inputs as they should be provided by the OGC API processes. And then we registered our process on the ADIS JavaPS instance and are now able to execute this very same process as I've done locally in my development environment on the web. So that's basically pretty nice. And I can also use that in our web client. Let's do a reload. So we have a plain client here, and the client allows me to add new WPS services. And what I forgot to say is that this ADIS not only provides the OGC API processes, but also provides a WPS interface. So same URL, we can retrieve the capabilities. We can take a closer look at the processes, and here we can see the same process which is available on the REST API we have here as the WPS 2.0 interface. And our client makes use of that. It is not not yet supports the OGC API processes, but in our case it doesn't matter because we can use the WPS 2.0 interface as well. And we simply add the URL here. Add it, and then we can select our process. Works as expected. We use the calculation of a geometry buffer using Jupyter notebooks, and then we are able to not again go to Münster, but we can also use here maybe Santiago, Chile. Oh, there is an image missing. Let's simply state I want to have my buffer here, and I define a buffer of maybe 8 kilometers. And everything else, I don't need to define anything else, and I can execute it. I do now a synchronous execute, and I want to have the response in document so the client can directly visualize the outputs. Executing. This is the final step. Hopefully everything works. Yeah, here we can see our buffer. Here's the icon again. And yeah, this is pretty much it. We have our JSON file here, a GeoJSON file. We don't have any properties here that can be visualized, but you can see that the buffer worked as expected. And yeah, basically that's the idea. We have Jupyter notebooks, and we can make this Jupyter notebooks run on the cloud and integrate it very easily with our existing software solutions. A few things to keep in mind. There is no actually defined interface between the application package and the execution unit. So at the moment, we developed a concept of our own, how to transfer the inputs and the outputs to the execution unit. So in this case, to the Docker image, and maybe I can demonstrate that in this Docker file. Shame on the tabs here. In this Docker file, we used prefixes and uppercase names of the inputs as defined in the application package as the so-to say interface. It's very similar to, for example, like Spring Boot handles environment variables. So we thought it's a de facto standard, so we went this way. So every input is prefixed with input, and after that with the name of the input, like buffer, radius, and meters, and the same way goes to outputs. So I think it's a pretty good solution, but there is no standard how this is defined in the ARDIS world. Yeah, and of course, Docker execution is most suitable for heavyweight computations because using Docker containers always brings in an overhead. You need to retrieve the image if it's not already on the environment. You need to launch it. So it is maybe a little of overhead for this kind of easy process like a buffer, but for big executions like analysis on multiple sets of satellite data, for example, this is a very nice thing to have because the overhead is not seen or doesn't play a big role in that way. What is the road ahead for our ARDIS implementation? So we want to do a feasibility study in established cloud environments. Does this work in the same way with, for example, a Kubernetes instance of the JAVAPS running in Google Cloud Platform or on AWS or something like that? At the moment, we have a virtual machine where a Docker backend is running, the Docker engine is running, it works perfectly fine. But in Kubernetes, things may look a little bit different. So we want to check if this works as well. And then we want to have a generic approach for notebooks. So as I said, this interface between JavaPS and the container execution should be improved a little bit to make it more flexible and maybe also to execute generic notebooks and not just the one that I defined. So we can maybe reference a notebook from outside and see if it works in the same way. And then we work on additional frameworks as well. R can also run on a Jupyter kernel or in Jupyter notebooks. So there should be a similar way to use this. And we will take a closer look into that. Okay, so looking at the clock, we have 10 minutes left. Let me do a very brief summary of what we've seen today. So Benjamin introduced geoprocessing in general and what the motivation behind that is. We have seen WPS.2.0 as an established standard. We took a look at OGC API Processes as the emerging next generation API or the next generation standard. We also took a look at client and server software, also in action. And then we just had this walkthrough tutorial style of how to set up your own process with Jupyter notebooks, Docker, and the ARDIS. So this is what we covered. At the end of this presentation, you can see some additional resources and some readings if you are interested. And this concludes our tutorial.